Hey everybody! In this video we are going to pick up right where we left off in the previous one. We were learning about vector functions, and so we looked quite a bit into how you define them and then their limits, continuity, derivatives, and now we're going to talk about motion in space, and so the motion of maybe an object or particle moving through space and a vector function that defines that path of that object or particle. So let's start with defining our vector function, r of t. So remember how this looked really quick. R of t was f of t I plus g of t j plus h of t k. So this was a function that you input t, that could represent time, and it gives you an output for I, j, and k, and then that represents a point in space. And so that point can be found from a vector, basically going from the origin to that point. And that's what this function is, this vector function. So what does this represent for our object that's moving? So this is the position vector. So position vector of a particle moving along a smooth curve. Moving along, oops, that says along, a smooth curve. Okay, so that's our vector function. It's the position of this particle. So now we took the derivative, or mentioned the derivative in the previous video. So r prime of t, the derivative of this function, from the previous video, remember, it was giving us a tangent vector at a point. It also told us the direction of the particle, but we can rewrite this as, of course you can use your notation dr dt, derivative of r with respect to t, but we tend to use v. Why v? Think about it. If you understand what this is telling you here, okay, if you take the derivative of the position of this object where it's at on its path, it's going to actually give you the, think of like rate of change or speed or velocity. Okay, so v for velocity. So this is the velocity vector, which is tangent to the curve. So it's tangent to the curve at every point that you take this derivative at. And I said this a moment ago, but it points, so recall how this goes, this points in the direction of, we'll say movement, of how the particle's going. Alright, now if I guarantee that this is positive, what does that represent? So the absolute value, or the magnitude of this vector v, the derivative of r, that one is speed. Okay, so let me write it like this first: magnitude of dr dt, and that is just the speed that the particle is traveling at. All right, so speed, and that the particle is traveling at. We don't have to write all that. So just to kind of add a little bit to this here, let's just say note the direction. So direction of motion at time t is, so think about it really quick. Actually, let me move up here so I don't run out of room. So is, just going to kind of go here. We learned about direction of a vector before, and the derivative will point in the direction of the motion. But if you want to have a vector that represents just that direction, you shorten the length to 1, and you say that that's the direction, and then you can multiply it by the magnitude, and that will give you the desired length. Okay, and so is basically the velocity vector divided by its magnitude. Okay, so this is a unit vector when you divide a vector by its own magnitude, and that represents direction. So it's length 1, and it's telling you which way your vector's pointing, and in this case, which way the particle is moving. Okay, now what if I take one more derivative? So my position vector was r of t. I'm just going to move this out of the way really quick so I have some space. My derivative of the position was velocity, and if I take the second derivative, some of you know what that is. So second derivative of r with respect to t, which is the derivative of the velocity. Let's just take off that vector notation. I don't want to make it look too crazy. That is acceleration. Okay, so A for acceleration. So this is the acceleration vector. Acceleration vector. So the second derivative of the position is how much your vector is accelerating at that point when you plug in t into the second derivative. Okay, let's go ahead and look at an example. Okay, so we want to write the particle's velocity. Particle's velocity at t equals pi over 2. So if this represents time, this is about 1.57 units of time. So we're going to write this velocity as the product of its speed and direction. And that's going to be if its position is given by the following. So I got to give you a function to work with. So I'm going to give you this vector valued function. So given by r of t equal to 2 cosine t I plus 3 sine t j plus 4 t k. Okay, so we need to do a few different things here to answer this question. Just identifying what's being asked of us, write the particle's velocity at this t value as a product. And the product has to be speed times direction. Okay, so identifying what we know that speed, we're going to need to find the magnitude of the velocity vector. The direction is going to be the unit vector of velocity, so v divided by its magnitude. Then we have the given position. Notice this is a position function, so we have to still find v by taking the derivative. So remember that v is the derivative of r. So the velocity is the first derivative of position. Okay, let's work these out. So we're going to start with the derivative because we got to get that to find speed and direction. Okay, so move this out of the way. And the nice thing about this is your derivative rules all still hold for vector valued functions. So everything you did before in the past, let's try that out here as far as derivatives go. So v of t, which is the derivative of r, we're going to just take the derivatives of each component. So right here, derivative of 2 cosine t is just going to be 2. Actually, if you want, you can write it out in steps. So let me just do that so it's very clear. Derivative of that, I, plus 3 sine t, that derivative, j, plus 4t, derivative k. Alright, now we'll break it down. 2 cosine t, derivative of cosine is negative sine t. So this is negative 2 sine of t, and this is still the I component. Middle component here for j, the derivative of sine t is cosine t. So 3 cosine t, and that's still j. And then the derivative of 4t is just 4, so this is 4. Okay. Alright, and this is v. Good. One part's done. We found the derivative. Now, we need to find the magnitude at this t value, and then also divide the vector we just found by its magnitude. Okay, so we're going to find the formula first for magnitude, and then we'll plug in the number. So I'm going to say magnitude of v of t. I'm just going to distinguish that I'm keeping t until I'm a couple steps later and we'll plug in the number. So this magnitude is square root of the components squared and added. So it's going to be negative 2 sine t squared plus 3 cosine t squared plus 4 squared, all under the square root. Okay, let's move over here. So let's see what I get. This is going to be square root of 4 sine squared t plus 9 cosine squared t plus 16. Alright, we are going to plug in our value for t, but what I want to show you real quick before I do is that depending on t, we will get different values for our speed or magnitude of our velocity. And so the way I know that is very quickly from just looking at the fact that there's t still present. This is not a constant number. So if you got one particular number, like t was no longer here anymore, then your speed would be constant. Your particle or object would be traveling at a constant speed. Because t is still present in this derivative, in this formula for speed, then it's going to change. The speed of your particle is changing depending on what t is that you plug in. Alright, so just wanted to note that for you. And so now we're going to think about t equaling pi over 2, and we're going to plug that in here. And so that will give us our speed at that t value. So let me just make some more space here. We know we're writing it as a product of speed and direction. Okay, we already have our function up there, so we don't need this. Alright, so then we're going to plug in, so I'm just going to rewrite it here actually. V of pi over 2, magnitude of that. So this is going to be square root of 4 sine squared of pi over 2 plus 9 cosine squared of pi over 2 plus 16, all inside the square root here. And let's start simplifying. Sine of pi over 2 is 1, so this is 1 squared times 4. So square root of 4 plus cosine of pi over 2 is 0, so this is 0 times 9, so that's 0 plus the 16, so this is square root of 20, which if you break that down, that's square root of 4 times 5, which is 2 square root of 5. Okay, so there's the speed. This is not the answer, this is just half of what I need to get to the answer, but that's our speed. Now we just have to divide the velocity vector by its magnitude to represent direction. Okay, so then the direction is v over magnitude of v, and we're going to do it at this t value. So here's my velocity vector up here, and so we have negative 2 sine t, I'm just going to put it in component form for now, comma 3 cosine t, comma 4, divided by 2 square root of 5. Now this is the direction vector, the unit vector pointing in the direction that our particle is moving. But I have to put these two together to answer the question. The product of speed times direction. So that times this. And you don't want to simplify because then it would defeat the purpose of it looking like a product. So then our final answer, v, okay, is going to be our speed, 2 square root of 5, times, let me move that out of the way, times this whole vector here. And feel free to kind of simplify some parts of this. I'll go back to IJK form now. So this is going to be negative 2 and 2 divide out. So this is going to be negative sine t I. And then nothing divides out for the middle component. So that's going to be plus 3 over 2 square root 5 cosine of t, and that's for j. Okay, and then last, 4 and 2 divide, so I'm going to be left with 2 on top. So it's 2 over square root 5k. And then that would be my final answer. So let me kind of get this out of the way. So this right here. And of course, if I multiply 2 square root 5 times each of these, I'm going to get back to, sorry, I forgot my square root 5 right here. Right there, square root 5. If I distribute, I'm going to get back to v, but that's the point, because v should equal itself. But we write it as a product. We write it as the magnitude times the unit vector, and then that way it's very clear what's what. This is the speed, or magnitude. This is the direction, but length 1, that the vector is the particle is traveling. Okay, let me give you a fact about when you have a position function that's constant, and then we'll do one more example. Okay, so here's this fact. If the magnitude of the position vector is constant, so remember that would represent length. So if the length of your position vector is always constant, then the following is true. When you dot the position with its derivative, you're going to get 0. Okay? And then think about what you know when you take the dot product of two vectors and you get 0. So this means that the position vector, r of t, so the position vector, and what's the derivative of position? Velocity. So the position vector and the velocity vectors are perpendicular or orthogonal. Perpendicular. Okay, so just so you can think of what this might look like, so the position vector, it starts at the origin and ends at the point in space where your object is at. So this might be like maybe your particles moving around a sphere. Okay, if your sphere is centered at the origin, think of that. So every point on the sphere would be the same distance away from the origin. So if your particle is moving along like that, that would be this example, or an example of something like this, where the length of that vector is always the same value. And so at every point on that sphere, if I kind of just draw that real quick, at every point on that sphere, so your origin is here and your vector r is there, the derivative, remember the derivative is tangent to that point. And so the velocity is this derivative and it's tangent to the sphere, and so this is going to be perpendicular. It's going to create this 90-degree angle. Okay, so just an interesting fact to mention for you. Now let's go through this example here. So let me give you the following. So given that r of t equals natural log, so ln, natural log of t squared plus 1, and that's going to be I, plus tangent inverse of t, and that's going to be j, plus square root t squared plus 1 k. Find the angle between the velocity and acceleration vectors. Between the velocity and acceleration vectors, and this is going to be at t equals 0. Okay, so I picked this one to show you because it looks like a lot's going on. 3 different types of component functions here: natural log, inverse trig function, and a square root function. So a lot of things going on. So just sort of reminding you of your derivative rules as we go through this. Okay, so we have a lot to do here. We are asked to find the angle between two vectors. Okay, so that's going to require some past knowledge. But notice also that the vectors come from derivatives of what we're given. We are given position. So I need my first derivative for velocity and my second derivative for acceleration. So that's got to be my first 2 steps. Then we can work on the finding the angle part of this. Alright, so I'm going to go right into finding my first derivative, which will represent our velocity vector. So r prime of t is our velocity. And we can just start taking derivatives component-wise. So let's jump right in. Derivative of natural log of t squared plus 1. So that's going to be 1 over the inside, t squared plus 1, but we still have the chain rule. So times the derivative of the inside. So times 2t. Okay? And that's going to be the I component. Okay, so that part's here. Then tangent inverse. What's the derivative of tangent inverse? So this one is 1 over 1 plus t squared. And that's for j. Alright. And then square root here, derivative of the square root, we have, from the outside, if I rewrite this, this is, let me write it down here, t squared plus 1 to the 1/2 power. So the outside, I'm going to get 1/2 in the front, and then negative 1/2 in the exponent. And then the inside stays. Actually, k is not there yet. And then derivative of the inside, so times 2t. And all of that is our k component. Okay, let's make that look a whole lot better. So v of t equals, that's going to be 2t over t squared plus 1, I, plus 1 over 1 plus t squared, j. And then in the back here, there's a 2 on top, then a 1/2 here. So that those 2's are actually going to divide out right there. So all that's left in the numerator is a t. And then this negative exponent here, I'm going to bring that back down. It's a square root on bottom. So t squared plus 1. And that's for k. Alright. So there's our velocity vector. Found that. Let's keep going and find the acceleration vector. Okay, so let me get this out of the way just for now. And so I want the second derivative of position, which is the first derivative of velocity, which is acceleration. Okay, so we're going to have to use, if you look at our expressions here, the quotient rule for derivatives. So I'm going to work this out, but feel free to pause this. Try this out yourself using your quotient rule for derivatives. And don't forget chain rule while you're at it, and then we'll come back and you'll see if you got the same answer as me. So work this out. Take a few minutes. Okay, how'd you do? Might have took a few minutes. So I did write out a couple of steps. Here's what I got here. Here's my first step. So this is the very first step for using the quotient rule on the I component. I just set up the quotient rule here for derivatives. The j component, I actually could kind of take a shortcut from the quotient rule, just using the fact that the top was a constant. So I just used the negative exponent. So I said this is really 1 plus t squared to the negative 1 power. And I just used a chain rule for the j component. And then on the k component, I had to use the quotient rule again. So I did simplify quite a bit, and I got down here. So just double check with your work and see if you got the same thing. So we have this negative 2t squared plus 2 over t squared plus 1 quantity squared, and then so on. You might not have simplified the k component quite like I did, but I had a fraction over, like in a fraction, and so I kind of just avoided that notation by simplifying the k component this way. So this is actually a square root quantity cubed way back here. Okay, so we found all this. Let's see what we do now. If you remember, we were asked to figure out the angle between this vector and this vector at t equals 0. So what we're going to need to do is recall the formula from what we learned with angles between two vectors really quick. So I need to keep my my v vector, so let's leave that there. I am going to go ahead and erase my work for my a vector, acceleration. Let's get rid of that. And let me just write that here. That was acceleration. Okay, a of t. And then remember what you know about the angle between vectors. So theta, if we use theta to represent that angle, it's cosine inverse of the dot product of the two vectors divided by the magnitude of their products, or the product of their magnitudes, excuse me. So we have to dot these two vectors, find their magnitudes, and multiply those. But all of this is at t equals 0. So let's go ahead and plug in t equals 0. So I'm going to say velocity at t equals 0. I'm just going to kind of do it by talking to you guys. So this is going to be 0 in the numerator. Just make sure the bottom's not 0 because then it would be undefined, which the bottom's going to be 1. So this is just 0i. Over here, this is going to be 1 plus 0 on bottom, but 1 on top. So this is 1 over 1, so that's 1j. And then over here, 0 on top, just make sure the bottom's not also 0. So it's going to be square root 1, so that's 0k. Alright, and then let's see. Let's stick with v for a moment. We still need to find this magnitude. So magnitude of this vector is just square root of 0 squared plus 1 squared plus 0 squared, which is 1. Alright, let's move on to a. So a of 0, I'm plugging in a 0 everywhere. On top, I'm going to be left with 0 plus 2. On bottom, this is going to be 0 plus 1 squared, so with 1. So we just have 2 over 1, so it's 2i. Right here, the bottom is going to be 1 plus 0, and the top is going to be 0, so that's 0j. And over here, let's see, plugging in 0 everywhere. So let's start with the denominators, because I just want to make sure they're not undefined. So this is going to be 0 plus 1, so that's 1. 0 plus 1, that's 1. Okay, so now on top. This term, if I plug in 0, I'm going to get square root 1, which is 1. Back here, that's 0. So that whole term is going to go away. So this is going to be 1 over 1. So this is 1. Okay. Alright, I know I kind of did that fast, but if you want to write it out, I just plugged in a 0 everywhere I saw a t. Then the magnitude of this acceleration vector at time t is just going to be square root of 2 squared plus 0 squared plus 1 squared. So this is 4 plus 5, square root of 5. Alright, and let's put that all together. So we have actually let's find the dot product first, and then we'll put it all together. So I have to dot right here. I have to dot this vector with this one. I need v dot a, okay? And we'll just do it by pointing it out. So dot product, 0 times 2. The I components multiplied. I'll write that actually. 0 times 2. Plus the j components multiplied. 1 times 0. 1 times 0. And then plus the k components multiplied. 0 times 1. Okay, so that gives us a total of 0. Alright, a lot of work to get a 0, but that's a valid answer. Okay, so that's our dot product. And so if we plug this in to our formula up here, if I just change this to a's and v's, just so it's more meaningful for this problem, so this is v dot a over magnitude of v times magnitude of a. So this is going to be cosine inverse of 0 in the numerator, and the denominator is going to be this magnitude times this one. So 1 times square root 5. So this is cosine inverse of 0. You're basically saying what angle gives you a cosine value of 0. So if you remember how inverse trig functions are defined for inverse cosine, it's the angle between quadrants 1 and 2. And so cosine is 0 at pi over 2, or 90 degrees. So these two vectors for this function, the velocity and acceleration vectors, happen to be perpendicular because the angle between them is pi over 2, or 90 degrees. Alright, so that's it for motion in space. See you next time.